Abhinav give from IBM a talk that you've already heard a lot about, the sort of correspondence between fidelity and cross-entropy.
Okay, thanks, Bill, and all the other organizers for putting together this great workshop and for inviting me. And yeah, I'm going to be talking about a phase transition in this linear cross-entropy benchmark. And this is joint work with Braden Ware, Dominic Hangleiter, Pradeep Nirola, Bill Pfefferman, Alexei Goshkov, and Michael Gillens. Okay, let's begin. So one thing I really like about quantum computing today is that we have so many different architectures. And I think it's also fair to say that we don't yet know how quantum computing architecture of, like, say, 30 years from now is going to look like. And these architectures are all very diverse and different. And I think that's a really exciting time for quantum computing. But there's also a problem, which is that we cannot, the fact that these architectures are so different from one another makes it hard to compare them to each other. And yeah, we kind of sometimes lose a handle of what's really going on. And with these architectures, we have seen for the first time some evidence of quantum advantage over classical computation through these sampling-based experiments. Although, as Scott mentioned, that evidence is probably hanging by a thin thread. And one thing that's making understanding what's going on in these experiments really hard is the fact that we have noise, and we don't really know how things behave when we put a lot of them together. So that brings us to this idea of benchmarking. I should know that when we consider these random circuit sampling experiments, we have moved to a setting that's sort of native to the experiment. And because of this, we have gone away from the setting of decision problems and problems in NP, where we can efficiently verify. So I'm going to distinguish verifying a computation from benchmarking an experiment. And the reason is as follows. Imagine that you're an experimentalist. Now, I admit that sometimes it might seem the case that your experiment is behaving adversarially against you, but that's really far away from what really happens in nature. At least that's what we believe. So for example, yeah, when we build an experiment, we have a high prior against outlandish things, such as there being like a gremlin sitting inside your dilution refrigerator manipulating you. So we lose on our goal. So our goal is not really to convince a skeptic that something quantum is really going on inside here, but rather build our own trust and confidence in the quantum computer's components working well together. And first, it's like one metric, that is the fidelity, which is a notion of how close the state that you produce in an experiment is to some desired target state. And I should know that when we are talking about a quantity such as fidelity, we are inherently assuming that there is some underlying quantum state that we are producing. And in this sense, we are already moving away from the notion of some adversarial verification. Okay. So one problem with the fidelity is that it can take exponentially many samples in the number of qubits to properly witness. In fact, there are some sample lower bounds. And so an alternative that was proposed is what we've seen today, the linear cross-entropy benchmark. And it was proposed in these two papers. And I'll flash the definition again. So this is the linear cross-entropy benchmark, which I'll just denote the XCB or chi sometimes. And here P is the ideal probability of seeing an outcome X, whereas Q is what the experiment is really sampling from. And we have this normalization. And yeah.
So when you say exponentially many samples to witness, what exactly do you mean? Because I thought if I did shadow fidelity estimation, that's exactly telling me that I can do it with a few samples.
I believe there were lower bounds due to Henry Ewan, but maybe that's a different, that's probably a different setting. Yeah. Thanks. So yeah, for ideal quantum circuits, this is close to 1 with high probability, whereas when we are sampling from the uniform distribution here, Q, then we'll get a score of 0. And yeah, one nice thing about the linear cross-entropy benchmark is that you can sample efficiently compute it. So yeah, here you just replace Q with the samples that you see in the experiment, and that produces this estimator. Yeah. But I should note that, yeah, as Dominic mentioned in the previous talk, that this is still computationally inefficient to compute. So we still need to compute the ideal probabilities of these bit strings. Okay, so that's the XCB, and there are some nice things that have been claimed about it. So let's see. One claim is that if you have some noisy random circuit sampling experiment where your gate set is somewhat scrambling enough, then the XCB is the same as the fidelity. Also, it's believed that spoofing the XCB is at least as hard as doing even slightly better than random guessing. Although this was kind of disproven for like certain settings of shallow depth. Yeah, and that's what these works did. And in these papers, there was a justification given for why the XCB is a good fidelity proxy. And this works in something I call the low noise limit, which I'll get into soon. So the main question we want to ask in this talk is, when is this linear cross-entropy benchmark a good proxy for the fidelity? Okay, here's an outline of the talk. So I'll first talk about the white noise model, which again was brought up before, and how it justifies the XCB. And I'll give a quick preview of like the main results before I jump into like the techniques. Okay. Any questions so far? All right. Let's get into this. So our setting is as follows. We have so this figure is from Dalzell et al. We have a random circuit where, let's say, we have n qudits here, and the circuit has depth d. And we have locally random gates applied between qudits. And let's say at the end, before we measure, we produce a noisy output state rho. Now, the white noise approximation is just the same as global depolarizing noise. It says that this noisy output state before you measure is this linear combination of the ideal quantum state and a mixture of the completely uniform distribution. And so if this approximation holds, then the XCB can be a good fidelity proxy. And so Dalzell et al. Studied when is this a good approximation. So in particular, let's say they considered qudits with local dimension cube, and they considered these noise channels to be that of single qudit unital noise. And the noise strength is measured through either the infidelity R, which we'll sometimes rescale by epsilon, by this factor. Yeah, so just think of R and epsilon kind of interchangeably. It's just proportional to the noise strength. And all these works rely on statistical mechanical model. So it's a mapping from random circuits to some model in Stat.mech, which you can then study moments of. Okay, and I'll mention some prior works. So as I mentioned, Dalzell et al. Really studied this quantity first. And what they were able to show was that if the noise strength is it's order 1 over n log n. So this is what I called the low noise limit earlier. Then the white noise approximation works well for, say, quantities like second moments of your output probability distribution. Do you have a question? And yeah, they had some evidence that this could be improved to anything that's like some 0.3 over n. This constant is not that important. They also showed that in this regime, which I'm calling the low noise regime, the fidelity, the cross-entropy benchmark, and the distance to the uniform distribution, they all scale as exponential in the noise strength times the circuit size, which goes as ND. Meanwhile, at higher noise rates, let's say the noise strength for every channel is a constant, this work also showed that the cross-entropy benchmark breaks down in the sense that it doesn't reflect the fidelity anymore. And also our work with some others shows that in this regime of large noise, the total variation distance to the uniform distribution is lower bounded by a quantity that goes like exponential in the noise strength times the depth. So this is, these two do match when the noise strength goes as 1 over n. But yeah, so this means that this kind of scaling cannot go on forever as you increase the noise. And what this essentially means is that something qualitatively very different is happening in the regime of low noise and high noise. And that's what we seek to study in this work. Okay, so our main claim in this work is that there is some constant that depends on the architecture and gate set or whatever, such that if the noise strength, epsilon, is below C over the number of qudits, then the XCB is a good estimator for the fidelity. And if you're above this sort of noise threshold, then the correspondence between XCB and fidelity immediately breaks down. And the claim is that this happens as a phase transition. And as I said earlier, the location of this depends on the geometry of the circuit and what your gate set is. And yeah, I'm stating this as like a claim and not a theorem or something, because we rely on some numerical evidence, but we trust this numerical evidence.
But this is for which type of noise?
This is for any noise that's not leakage. So it turns out to also work for non-unital noise. It's like the same physics happening. So the upshot is that as an experimentalist, one should really read the warning sign before using the Cross-Entropy benchmark as a benchmark. Okay, now I'll get into the techniques and talk about this Stat.mech model. So we really start off with the oldest trick in the book. So we want to get expressions of the form ρ1 times ρ2, and we instead work with tensor products ρ1 tensor ρ2. I illustrate this with the fidelity here. So in the case where the noiseless circuit is pure, the fidelity is simply given by this expression. So it's the trace of these of the two copy states, and I can write that as a swap times this two copy state. And when I take the expectation value over random circuit ensembles, I can move the expectation into the trace, and I have this object remaining. So it all boils down to how this two copy average state evolves in the circuit. And we assume that in our circuit architecture, there's a layer of single qudit hard random gates after every gate. Okay, so what this does is essentially we end up taking expectation values over states of this form. And yeah, if you've seen this before, what this does is that you're effectively projecting down to the permutation symmetric subspace, which is spanned by, say, the identity operator, and this S is the swap operator between the two copies. And I've denoted them by, I've just normalized them by Q square and Q respectively, because I just want to work with trace one objects. And this is the formula that governs how the average works. Okay, so it just suffices to keep track of the average state. And now let me illustrate what happens for the XCB. So we again go back to what the definition of the cross-entropy benchmark was. It's this expectation. And yeah, I can just rewrite it as this. So I have a swap again, and I notice that I have two copies of the state with noise applied in one of the copies. So again, it suffices to look at how this object is evolving in the circuit. And this brings us to the update rules of this Stat.mech model. So if I start off with any product state, then the hard average over the single qubit states just produces this linear combination of the identity and the swap. And after this, what happens is that I can now just think about my dynamics as some classical random walk occurring over these bit strings that represent the average operator. So in fact, the average two copy state that I mentioned earlier is now just some, it's a distribution over, say, bit strings. And when we apply a two qubit unitary, we have the following update rule for the Stat.mech model. So the identity.
Can you please remind what's S?
S is the swap operator between one copy and another copy that we had.
There's no mentioning here of the original state.
Yeah, no.
So
So let's say we had, here I'm assuming that psi was a product state on every qubit. And we are just averaging over like one layer of hard random gates on that.
okay, so the right-hand side is independent.
It's independent, yeah. Yes. Yeah, so under these update rules, what happens is that a state that was identity, which I denote as 0, 0 here, still gets mapped to a 0, 0. Whereas if I had swap in like occurring as some term in the combination, then that is also preserved. So 1, 1 gets mapped to a 1, 1. This is the more interesting update rule. So if I have a 0 and a 1, or a 1 and a 0, they get mapped to a combination of 0, 0, and 1, 1. Okay. So I'll describe what's going on in the physics of this model. So under application of unitaries, we have these update rules that I just mentioned. And one can easily observe that the bit strings that are all zeros and all ones are fixed points of the model. So if I have all zeros, then it'll remain all zeros. That's what I mean by fixed point. And this means that there's like a unique fixed point state at really asymptotically large depth, which is given by the following combination of the all zero string and the all one string. This expression is the same as if you took a Haar random state and did this 2-copy average. Okay, in the presence of noise, the physics of this model changes. And yeah, let's say we have, again, noise strength R measured in terms of the infidelity. What noise does is it keeps the identity the same, whereas a swap operator decays to the identity with some probability that's proportional to the infidelity of the channel. So in terms of this bit string notation, a 0 is still a 0, whereas a 1 decays to a 0 with some probability here. And what this means is that when we have noise, this state, which was the all one state, is no longer a fixed point. So we only have one unique fixed point now, which is this all zeros state. And yeah, that leads to a decay in both the fidelity and the XCB. So in particular, let's denote by x, like the magnitude of x, the Hamming weight of a bit string x. So it's really counting how many swaps are there in this representation. Now the fidelity, it turns out, is given by the following. So you look at the probability distribution over these bit strings that I mentioned earlier, and you weight them by q to the twice the Hamming weight. And then, yeah, you have this q to the minus n factor. So the XCB is also another observable that depends on this probability distribution, and it's morally very similar looking. We are still looking at Hamming weight, except we are just raising it to q to the x instead of q to the 2 magnitude of x. And one can see that under these unitary update rules, the fidelity is conserved under all these updates, and the XCB tends to evolve to 1. And yeah, as I mentioned earlier, in the presence of noise, so the final state is given by this. So that would mean that the final fidelity is like q to the minus n, and the final XCB is 0. Okay, so that was a brief description of what the physics of this model is. And I'll now talk about some numerical results. And so what we did was simulate this Stat.mech model.
I'm confused about the mapping. So the mapping is between some average over the random circuits to the statistical model?
Yes.
What exactly, what's the exact statement?
Yeah, so these are the exact sequence. Like we take an expectation over the ensemble of random circuits.
Under the same mapping, you can map the expected fidelity as well as the expected cross-entropy benchmark. But what else? Is it?
We can do other two-copy observables. So, for example, we can, when we write the purity, we'll have to put the noise in both copies. That would also evolve under similar rules, but yeah, we just we now put noise in both.
Is there a general claim about like what kind of quantities can you map? That
we can do
that you can map any expectation over any quantity for this statistical?
Any second moment quantity.
Any second moment quantity. And can you extend it to 3 copies and third one, or something like that, or?
In principle, yes. Although the update rules, I think, get a bit messy. So we simulated this Stat.mech model for reasonably large system sizes, and they were extremely precise. Well, I should mention that I wasn't the one who did these numerical simulations. It was Braden. And the way it was done was through like a tensor network representation of the classical probability distribution. And I would like to delineate what's rigorous and what's not. So the expectation value of fidelity and XCB, that can be written exactly as some observable of this Stat.mech model. And then we have done numerical simulations of that Stat.mech model, which could perhaps be viewed as some heuristics. So one more thing we exploit is Hamming symmetry. So in particular, when we consider an all-to-all architecture, meaning that we have no spatial locality constraints, and so in each layer, we apply just a random gate between any 2 qubits. What happens is that when we average over all possible pairings of qudits and the gates themselves, then the update rules depend only on the Hamming weight. So in particular, we are just left with a rule like this. My bad, this was a 2 goes to 2. And the noise update rule is also similarly Hamming symmetric. So the upshot of this is that now a random walk occurs only in a space of, say, n+1 dimensions instead of 2 to the n. And this means we can access really large n. So let me show you some numerical results for the fidelity. So it starts at 1 and decays very quickly as.
You said tensor networks earlier.
Yeah.
Why do you need it to do it like that? There's no structure for tensor networks anymore if you do this pattern.
It turns out that like we could have just done like a Markov simulation, and that's what I was doing, in a very happy way. But because the fidelity observable, it depends exponentially on the Hamming weight. It turns out there are like very few instances that contribute by like a really large factor, and then you always tend to undersample. So if you want like a really precise handle of what the fidelity is, it turns out that these distributions can also be well approximated by low one dimension.
Okay.
The tensor network just like taking the state, like the vector of probabilities for each Hamming weight, or so what is it? Maybe going off this question, like why is the tensor network better than just give me a list of all the.
So a list of all the entries were, yeah, like take memory like exponentially.
I thought you did this mapping down to like n+1.
Oh, okay. Yeah.
Wait, yeah, I want to store n numbers or n+1 numbers. And
Yeah. Okay. We also do like
my point is that
1D
I don't see once you have a Hamming weight representation. I mean, there is no natural like 1D or whatever structure you should use for tensor network. It's completely gone. That's, I mean, before you do that mapping, I see how you use tensor networks, right? But after that, like, seems a bit.
yeah, no. So for the all-to-all, we don't really need the tensor networks, but we also did it in 1D, for example.
Okay, but then without doing the Hamming weight.
Without the Hamming.
Okay, then I see how it works. Right?
Yeah, so this fidelity decays really fast at first as like 1 minus epsilon to nd. So I'm looking at fidelity versus a rescale notion of depth. So it turns out that different noise strengths all collapse onto this same curve. And then they decay until you hit this floor of q to the minus n, which is really the lowest you can go. In fact, there's still some deviation away from q to the minus n, but that's not so visible here. In fact, it goes as q to the minus n plus something that's still exponentially separated away from q to the minus n. Okay, let's look at XCB now. So it turns out that the XCB behaves as follows. When you have low noise strengths, the XCB decays pretty similar to the fidelity. So this black dashed line is how the fidelity decays. But beyond a certain noise strength, there's no correspondence anymore between the fidelity and the XCB. In fact, there's probably a stronger claim, which is that the decay rate of the XCB is now not reflective at all of any inherent noise strength in your system. So let's look at this asymptotic decay rate of the XCB, which is essentially the slope of this line. And that shows this following feature. Again, at low noise strengths from like 0.45 to up to 0.9, the decay rate of the XCB depends on the noise strength. But after a certain noise strength, all these deeper shades of blue, they all converge to this line. So the XCB decay rate is a function of noise for a small noise, but is noise independent after that. So, okay, we ask whether there's a transition here. And it turns out that the slope, which governs the decay rate of the XCB, looks like this. So we think there's a sharp crossing here at something like 0.92. And because we have done this Hamming symmetry, we have gone to this Hamming symmetric subspace, we can actually compute the eigenvalues of the transfer matrix that.
It's true that in the white noise approximation, the cross-entropy and the fidelity are the same.
Yes.
For any amount of noise. So how come you don't have any dependence on the distance from the white noise?
So in the.
I mean, if your noise is white noise, then the transition, then there is no separation between the fidelity.
Yeah, so what's really happening is that the white noise approximation itself is breaking down at.
But you didn't, I mean, you cannot break down unless you say that your noise is far from the white noise, right? Or oh, you're saying you're assuming local noise, and the very approximation of the white noise
Yes.
breaks down, regardless of the nature of the noise.
Right.
Also for local white noise.
Yeah, like even if you have local
Yeah,
depolarizing.
deeper. Thanks.
Yeah, previously we only had guarantees that the white noise approximation works when the noise strength is like 1/n log n. Yeah, and we are no longer in that regime. Yeah, so we can also confirm this picture using the fact that we had this Hamming symmetric subspace, and we can actually compute the eigenvalues of, I guess, the transfer matrix that governs the update rules of the probability distribution. And we find that the decay rate of the XCB is well characterized by what the leading non-zero eigenvalue here is. So for small noise rates, the XCB decay rate is given by this curve here until it crosses here, and after that it remains constant. And yeah, so this leads to an estimate for where the transition should be, which is epsilon n something like log of 5/2. And yeah, so there was this recent paper by Morvan et al. Who claimed that this transition in XCB also corresponds to a transition in whether the XCB is spoofable or not. In fact, they also saw the XCB transition I mentioned earlier experimentally. And yeah, like I just want to think a lot about whether there's any hope of proving such a transition in complexity. And like we can look at both the easy side and the hard side. So on the easy side, we'd like to show that if the noise strength is larger than some constant over n, then this Gao and Duan algorithm that was recently analyzed better in this paper, we would like to show that that works. But the problem is that it has a runtime that scales exponential in 1 over the noise strength. And in the regime that we are working with, where of low noise, this would have a not so good scaling. On the hardness side, we would like to show that at sufficiently small noise strengths, using the fact that there is a white noise approximation to the probability distribution, yeah, we can justify hardness of sampling.
Empirically, I mean, how sharp does the transition look like? Like, is there a particular constant C such that a phase transition happens at C over N? I mean, for the spoofability, I mean?
Oh, for the spoofability,
yeah.
It depends on whether there is a phase transition in the first place.
Sure, but you said that someone argued that there seems to be one.
Yeah, that's right.
So what are they seeing in their data? Are they seeing like a sharp as you adjust the error to like C over N, that at some value of C it jumps, or is it just that it's smoothly, you know, as you adjust C it goes from one regime to the other regime?
Yeah, I do recall some plots where they look like, yeah, there's some crossover, and like the points at which various curves intersect seems to be independent of system size, but yeah, I think there are smallish numbers of qubits. So
Yeah,
maybe I
really
might
tell.
have an answer because we're on the paper, right? Yeah, so that brings me to the end. So we have seen, so this is a study of when the XCB is informative and when it isn't. And this is hopefully a way of comparing different experiments. And yeah, so we focused on this low noise regime in this talk. Can you get anything at constant noise? One issue is that at constant noise, the fidelity decays very fast to the minimal value. So at constant depth, you're already very close to q to the minus n. And actually, this is also why the fidelity doesn't really witness the transition. Because by the time the transition is has occurred, the fidelity is also already very close to its minimal. And there's some things I didn't tell you about, which is that, yeah, we have a prediction for where this transition occurs. And that comes from this analysis of how the eigenvalues of the transfer matrix look like. It turns out that the entangling power of the gate set is a very important notion. So we'd like to improve this prediction to other circuit architectures, like, say, d-dimensional lattices. And yeah, as I mentioned earlier, for non-unital noise, the Stat.mech model is morally the same, and like the same physics goes through for these fidelity and XCB observables, which are just observables where you have noise in one copy of the state. But if you're looking at other quantities like the noisy collision probability, which is related to purity, then the physics is different. And yeah, there's some work in this direction of non-unital noise by Pfefferman, Ghosh, and others. Yeah, and are there other ways of bringing these calculations closer to what is really being done in experiments? One other feature that experiments have is like, yeah, they don't really consider high random single qudit gates, but instead gates chosen from some discrete set. So yeah, that might or might not change some of the things we see here. Yeah, that's all. Thank you.
Yeah. You started out by talking about experiment. And it seems to me that if I was an experimentalist and I wanted to know what the fidelity of my quantum computer was, I would do something like, if I had run it for a certain distance, then I would invert the circuit and see what the fidelity is, get all zeros again. And that would be a very good measure of the fidelity of my hardware. Or I could run Clifford circuits. I mean, there are so many things you could do that could check the fidelity, which are not of this nature. And then you could ask whether, you see, this cross-entropy is only good when the output distribution is very flat. Otherwise, you're never interested in it. So then you could then say, when I'm running it in a manner that produces a flat distribution, is it matching what I'm getting when I run forward and back? It seems that there are so many ways that experimentalists would check this without mentioning anything of the kind of things that are being discussed by computer scientists or anyone else. We just measure it. Am I wrong? Am I missing something?
Well, two things. One is calibration errors.
Oh, yeah, that could happen.
So if you're like
Calibration
over-rotating consistently,
fair enough.
then yeah, once you undo it, you don't see that.
Yeah, fair enough.
Another is the fact that we have these really nice analog systems where we don't really have as much controllability as the experiments you mentioned. So I feel the XCV can be a good way of comparing different architectures with one another.
Okay.
So for your point about non-unital noise, why do you say that the physics changes depending on whether you're looking at fidelity and XCB versus the equivalent formula?
Yeah, it has to do with the updated rules of the Stat.mech model. So when you're only applying noise to one copy, what happens is that after you do this random averaging, the identity is still mapped to an identity. even though the noise is non-unital. But once you have non-unital noise in both copies, this is no longer the case. And
So the thing is that like for the two things that as you say the physics changes, you have noise in both copies.
that's right.
Yeah, so two things. First, haven't you kind of killed the XCB? Because if you really believe this, then when you get to sufficiently many qubits, you're always in the easy regime. Because we would describe this as a transition in an unconventional scaling limit, where you actually have to scale up that.
Right. Yeah, so one thing is that you can be interested in the XCV in even if you are like, totally uninterested in complexity, right? Because you just want to know how your experiment is doing when you are putting in more and more components together.
So then it's just a prediction for what it should look.
Yeah, and if you have sufficiently low noise, hopefully, this can give a way of predicting where the transition should occur. So if you know you are likely below that threshold, then you can trust it in the XCB.
And the second question, is it still 1 over n in the all-to-all case? Because that's for the local case, right? So I would think it's a faster power for the all-to-all.
No, it turns out it's the same for all. Wait, when you say faster, you mean like even lower?
Even lower.
No, yeah, 1 over n is good enough. Yeah. Because I think one way to look at it is that in each layer we are still applying. So in this particular model, we are still applying like theta of n many gates in each layer because we are randomly pairing like qubits, and so it is scrambling fast enough.
What's the physical, is there a physical meaning for that?
What kind of answer are you looking for? Like what?
I don't know, that's interesting.
Well,
I mean, something is happening there, and cross-entropy benchmark is a quantity that is very computer sciencey, to take Eddie's words. I don't know, there's something physical going on there. What is going on there? Why is there a phase transition there?
yeah, I don't know. It's a very interesting question. I think perhaps as we pointed out, like it's a somewhat unnatural notion in the sense that physicists don't really like to, look at noise like 1 over n kind of scaling.
Yeah, but I mean, it
But-
appears in a variety of
Yeah,
cases.
there's something happening here.
No, but even these analyses of noise, for example, there is a phase transition in the multiple graphs with random edges.
Oh yeah.
Exactly. So transitions to chaos happen at the same scale. That's why.
I'm sorry.
Transitions to quantum chaos happen at the same scale. And in the past, people have said they're unphysical because it's such a weak perturbation you have to do to go from order to chaos. But it's the same kind of transition, right? It's a large random graph. You can think of it and you're just anything. So they are common. I think it's also a very specific transition to the cross-entropy benchmark, right? So so if you look at generic two-copy quantities, you would see the same behavior as the fidelity. These would also couple to the
Yeah, it has to do with how the fidelity and how the XCB really couples to the observables that are of interest here.
I don't know, it seems to me like it cannot be very isolated just to this case. There's something. I don't know.
Yeah, I think it's a very interesting transition. And yeah, this is our first study of it.
Oh, I have a question. So when we studied 1D, we studied sort of all to all. But
Yeah.
of course, what we really care about is probably somewhere in between that,
That's right.
2D, whatever. And I think just by us taking a poll, it seems like most people believe that for 2D and so on, the same thing should hold. But can you tell us any sort of better reason about why would we believe that? And it's just sort of hard to calculate, or do you think it's interesting to look into that, or not? Or can you help us out?
Yeah, so if you imagine a large 2D system, like what the Stat.mech model there is doing is really updating, say, I guess, bit strings that are like the bulk, so to say. The boundary can affect the physics of it. But yeah, I think, we believe the physics to be dominated by the bulk and a similar transition to.
So the constant would change.
The constant would
But
change.
it would be still a constant, and there's a phase transition and so on.
Yeah.
It'd be interesting to look into that. Anything else? Okay, should we take a break?